This video is on exceptions to the octet rule and the strength of covalent bonds, bond lengths, and bond dissociation energy. So, okay, so while we know that the octet rule, which says that all atoms need 8 valence electrons to be stable, is in fact a rule that is followed a lot in chemistry, there are exceptions, and we have to be aware of those exceptions. And because, like most rules, there are always some exceptions. So the 3 that we need to be aware of are when we have an odd number of electrons, when we have less than an octet, and when we have something called an expanded octet, which is more than 8 electrons. Okay, so the first one is kind of an odd situation, obviously, is when we have an odd number of electrons. So an example would be something like, NO. And if you were to attempt to draw a Lewis structure for this, when you do your electron count, the first thing you realize is that there are 11 electrons, and that's not a mistake. And no, it's not NO minus, it's just NO. It's a real thing. And knowing that it only has 11 electrons, you should know from the beginning that you're not going to achieve an octet. There's no way. So if you start, we can get a little bit better than this. We could have something that looks like this. We could also have it the other way, where N had the octet and O didn't. Okay, but no matter what, there are situations where we will discover that you cannot have an octet of electrons, and yet these compounds still exist. And so this is something that actually does exist. I think this is what's formed when, lightning strikes, I believe. It's a true compound, but it just has an odd number of electrons, and for whatever reason, it's okay. It's just one of those weird exceptions. So that's one we hardly ever see. The next 2, though, are much more common, and you'll see them appear in Lewis structure practices. And so the second one is when we have less than an octet, and so this most often occurs with 2 elements, and that is beryllium and boron. And so, like, if you were asked to draw the Lewis structure for BF3, so you think about, okay, boron would be in the middle with 3 electrons and 3 fluorines, each with 7. It works out, it looks like a really nice structure until you realize that, darn. I was just trying to get rid of that dot. That looks like, okay, that as drawn, it looks like it's perfect until you realize that boron only has 6 electrons. So while this is actually not the case, I mean this actually is the case, and you might be thinking, well, couldn't we draw this structure with an octet? And actually you could, because you could draw, instead of single bonds, you could do this. And the electrons work out, but this, however, is actually not the correct picture, and that's because of formal charges. However, just keeping in mind that beryllium and boron will be the ones who will violate the octet by going under 8 electrons, and they're stable compounds and they exist, and it's just how they are. And the ultimate reason is because it is based in formal charge. For beryllium and boron having less than 8 valence electrons. And then the other really common one that we see is an expanded octet that has more than 8 electrons. And this often occurs, with sulfur and phosphorus. There are other exceptions as well, but these 2 are quite famous. One of the most famous examples is sulfur hexafluoride, SF6. This is the gas that if you inhale it, unlike helium that makes your voice high, this makes your voice really low, deepens your voice. So if you were to, just for sake of time here, I'm going to do it. If we're to draw a Lewis structure, something we've never seen before, because in this case, sulfur has way too many electrons. Sulfur has 6 bonds times 2 electrons. That's 12 electrons for sulfur. But again, this is a real thing, and this truly is its structure, and it has an expanded octet. It's because of the three d orbitals being close by that can occupy these extra electrons. That's why it happens. But it's important to know that it happens most of the time, if it's going to happen, with sulfur and phosphorus. Now, this doesn't mean that anytime you see a sulfur and a phosphorus, it's going to be an octet exception. That's not what we mean. It just means that if it's going to happen, most of the time, it's with those two. Okay, and then a last kind of summary of some things we've discussed. I'm going to use carbon as an example. So I'm going to use carbon as single bond, carbon as double bond, and carbon as a triple bond. Now, I know these are incomplete Lewis structures, but I'm just attempting to say a single bond, a double bond, and a triple bond. Okay, so if I had to, we've already discussed this, and that is, which of these three has is the strongest bond, and that's a triple bond. So bond strength looks like this. Okay, the triple bond is stronger than the double, which is stronger than the single. And that, going along with that, would be something called bond dissociation energy, which is the energy to break a bond. And it only makes sense that if the bond is stronger, it takes more energy to break it. So those are two of these kind of trends here. And then the only one that we have had yet to discuss truly is bond length. And we've talked about that triple, single, and double bonds have different lengths, but we've never talked about that it actually, the triple bond is the shortest, followed by the double, followed by the single being the longest. And that's because if you think about a triple bond has 6 electrons that are pulling the atoms closer together, so it has a shorter distance in between those atoms versus something like a single bond that's only attracted by 2. So that's a very short discussion of octet exceptions. Again, keeping in mind that while most of the time the octet rule is followed, it's not always. And it can be broken by having an odd number of electrons, less than an octet with things like beryllium and boron, and more than an octet with things like sulfur and phosphorus. And then keeping in mind these 3 kind of trends and how bond strength, length, and dissociation energy